Low Earth orbit is becoming the most congested highway in human history. A single unmanaged collision can trigger a cascade of debris that makes entire orbital shells unusable for decades, and current ground-based avoidance systems simply cannot scale to handle it. This is Dhruva CDM, an autonomous constellation manager built for the National Space Hackathon 2026. Let me walk you through what it does. This is the ground track view. Every satellite in the constellation is live on a Mercator projection. The solid trail behind each one is 90 minutes of orbital history. The dashed line ahead is the predicted trajectory computed from the live state vector. Ground stations are overlaid across the globe because a maneuver command can only be uplinked when a satellite has a line of sight to a station. That constraint is enforced automatically by the scheduler. At the bottom, we can see a maneuver timeline. The maneuver timeline at the bottom logs every burn, every cooldown window, and every rejection in real time. When a command gets rejected, you can see exactly why: thermal cooldown violation, insufficient fuel, no line of sight. The validation pipeline catches bad commands before they even reach the thruster. We also have a 3D orbital view. Switch to 3D. The CSIM renderer gives you a full worldwide perspective. The entire constellation simultaneously at orbital altitude. You can rotate, zoom, and inspect any satellite. When a satellite drifts out its nominal station, keeping box after an evasive burn, the system flags it and automatically cues a recovery trajectory to bring it back within tolerance. The red spots below each satellite are blackout zones. The conjunction bullseye model. The conjunction bullseye is a polar plot centered on the selected satellite. Radial distance encodes time to closest approach. Angle encodes the relative approach vector. Debris objects are color-coded by risk level. Green is safe, yellow is a warning, red is critical. When something goes critical, the system doesn't wait for an operator. It calculates the evasive burn, validates it, and schedules it automatically. Now we can go to the burn logs. The burn log is the full engineering audit trail. Every autonomous evasive burn is automatically paired with a recovery burn scheduled to restore the original orbital plane once the conjunction window has passed. The entire sequence, detect, evade, recover, happens without a single operator command. Let's take a look at the fleet fuel. The fleet fuel analytics per satellite propellant budgets for the entire constellation is tracked continuously. The graph plots total delta V consumed against collisions avoided over time. These are the two metrics the system is constantly balancing: minimize fuel expenditure, maximize fleet uptime autonomously in real time. Let's come to the graveyard orbit. And if any satellite's fuel drops below the critical threshold, the system doesn't let it become uncontrolled debris. It automatically plans and executes a disposal maneuver to a designated graveyard orbit, and the satellite status transitions through every stage right here on the screen, so operators always know exactly what's happening. The system also ships with the time warp engine. You can accelerate the simulation forward, compressing hours of orbital mechanics into seconds, and the conjunction pipeline keeps running, keeps assessing, keeps scheduling burns ahead of real time. This is how you stress test the system, validate future conjunction windows, and verify that recovery trajectories actually hold up over the next several orbital periods, all before anything happens in reality. Autonomous conjunction screening, physics-accurate propagation, real-time evasion and recovery, full operator visibility across every view. Everything you've seen, the full stack, Docker setup, API documentation, and dataset files is available on the repository at github.com/jeevankumarm/projectdhruva. Clone it, run one command, and it's live. The README has everything you need to get started. Thank you.